Morad is the head commercial biomarker strategist here at Alistair. Leads a scientific and technical development biomarker discovery platform and solutions for axial VOC sampling and analysis. He holds a PhD in nanobiology and his postdoc research focused on understanding the origins and biochemistry of VOCs, mainly in respiratory disease. Over to you, Morad, and thanks.
Good morning, everyone. My name is Morad Nakhleh. I am lead biomarker discovery scientist at Owlstone Medical, and I am very pleased this morning to present to you the breath biopsy OMNI Assay, our signature platform for global VOC analysis and biomarker discovery. Our mission at Owlstone Medical is to save 100,000 lives and 1.5 billion in healthcare costs. And this is through the provision of clinically valuable breath-based tests that could be integrated in clinical practice for early detection of diseases and precision medicine. However, the first step in this journey still heavily relies on our ability to discover and validate clinically valuable breath biomarkers. Now, in the last 20 years, the global breath research community has focused a lot on trying to answer this specific question. Do breath biomarkers exist? Could volatile organic compounds represent biological signal and be objectively measured as biomarker of disease? Let's take a look into some key facts related to this question. The first, we know that exhaled breath is a very rich biological matrix. It contains organic, inorganic, volatile, and non-volatile, endogenous, but also exogenous compounds that not only reflect on the status of the lung fluids, but also mirrors the chemistry of the blood. Breath biomarkers already exist. I mean, CO2, hydrogen, methane, nitric oxide, and others are already in clinical practice. We know about hundreds of VOCs and their links to biological and metabolic pathways, such as aldehydes in oxidative stress and ketones in glucose metabolism. We've seen dozens of clinical trials that ended up with promising results and potential biomarkers in a wide range of diseases. However, there is still massive lack of success when it comes to replication or validation of those results. And that, of course, impacts the translation to clinical use, where we see it very limited to almost absent in terms of VOCs as biomarkers of diseases. Now, that could indicate a limited potential of VOCs to be biomarkers of diseases. However, that also could indicate challenges in the field that we need to tackle first in order to improve the chances of translational aspects of VOCs being biomarkers of diseases. Now, it's no secret that the field has been associated with historic challenges that negatively impact the reproducibility and reliability of results. In 2007, a review written by Anton Amman's group stated, analysis of exhaled air is not currently being used as much as it could be, because of difficulties in the methodology, sampling and analysis, and lack of basis for data interpretation. There are no normalized systems for sampling, thus making it difficult to interpret the results. However, and very unfortunately, even today, when we look into the literature, we still see the same messages about the lack of standardization again and again. In 2019, this is likely due to the lack of standardized equipment for breath sampling, standardized collection methodologies, as well as appropriate controls for potential VOC contaminants. 2021, just a few weeks ago, challenges such as standardization still need to be addressed in order to reach clinical validation. And therefore, the OMNI Assay was developed as a fit-for-purpose end-to-end breath sampling and analysis platform with a focus on tackling those historic challenges. So the first is to provide a high reliability and reproducibility of sampling, because otherwise we introduce a huge variability that could mask any biological signal, to provide a high analytical stability and consistency, to eliminate the chances of bias and drifts over time that could impact the reliability of output of large clinical trials. And of course, the elimination of contaminations and false discovery, compounds that might end up in breath sample, but their main source was never exhaled breath. Those might end up in our statistical analysis and showing us what is known as voodoo effects and faces in the clouds. We do that by using the state-of-the-art sampling and analysis technologies. On the breath collection side, we use the receiver breath sampler for reliable, reproducible sampling, with Casper for provision of cleaned inhaled air during the sampling session, minimizing the contaminations, and those are controlled by the breath biopsy collect software. On the analysis side, we use TDGC high-resolution accurate mass Orbitrap system to maximize the sensitivity to get the broader linear dynamic range and reliable identification of volatile organic compounds on breath. Now, we took the philosophy of the OMNI assay and translated that into two key requirements. The first is we need to provide a platform for global detection of exhaled VOCs representing biological signals, which means we need to maximize the range of detectable VOCs by the platform, but we also need to ensure that those VOCs are on breath. In other words, their main source is actually the human breath. The second key requirement is we need to have the ability to quantify changes happening in that biological signal, because this is what biomarker is. And that means we need to minimize the process variability to expose that biological signal. We need to minimize the error introduced pre-analytically and analytically to see the true biological signal. Now, we know that when we analyze breath samples, we see hundreds, if not thousands, of volatile chemicals in our chromatograms and in the final output. However, not all of those have the potential of being biomarkers. Compounds that are not coming from breath cannot represent biological signal and therefore cannot be biomarkers. Now, when we quantify a volatile organic compound in breath, what we are measuring is the total quantities of that VOC coming from all different sources and ending up in that sample. And those sources could also include ambient contaminants, what we inhale, traces on the tubes, contamination in collection bags or the hardware, or even during handling, VOCs could leak into those samples and produce false peaks. So in some cases, all we're looking at are basically contaminants, like in the right hand example. It's only the gray or the undesired sources of VOC ending up as a peak or a compound on the chromatogram. In other cases, there is a breath a signal with a wide range of signal to backgrounds. As the one in the middle, it's a poor signal to background, which means the signal is dominated by the background, while the one on the left has a massive signal to background, which means it's actually on breath VOC. And the distinction between those is very, very important. And I'll show you why in few examples. In this experiment, we collected 35 breath samples from volunteers as well as representative system blanks. Those blanks are meant to capture all of the undesired sources of VOCs that might end up in breath samples. Now, you could easily see that for isoprene, for example, the vast majority, if not all of the signal is actually coming from breath, since it is absent in the blanks. Thus, it is on breath VOC. And therefore, changes in exhaled breath concentrations of isoprene are expected to be well quantified by our platform. Now, to test this, we collected double the collection volume, and that translated into a good and obvious response by the system, as you could see on the right side. However, it wasn't the case for 1-butanol from the same experiment. As you can see, there is no much difference between the concentration of breath and the blanks. And thus, we cannot claim that this compound is actually coming from breath or could represent a biological signal. That also translates into a very poor system response. When we collected double the collection volume, we barely saw 5 to 10% change in the concentration. And this is what is expected by VOCs dominated by the background contamination until we improve their signal to background ratio. By the way, there was statistical significance when we compared the breath and the blank concentrations of one butanol, which is a very common method used in the literature nowadays to provide some sort of evidence that the compounds actually coming from breath. However, I think that this data and these results are evidence that this approach is not robust enough to make that determination. Therefore, we started by defining on-breath VOCs as the VOCs that their concentrations across different samples are at least 3 standard deviations above the mean representative background. We also defined a standardized way for testing and reporting the results, which we call the BOP study or breath or blank, in which we take, as I showed you before, repeated sample from a single volunteer, or we sample a small population. We also collect equal number of representative background blanks. And for each VOC, we determine if it's on breath or not based on this formula. And for every BOP study, we report on the same metrics, the number of on-breath VOCs detected across samples and their variability. We used those specific metrics all along the development and testing of the OMNI assay, allowing us to make decisions regarding the configurations and settings of the platform. And the goal was all along the way to choose the settings that would increase the number of on-breath VOCs that we repeatedly detect across samples and minimizing the variability of those compounds. Now, the first thing I would like to discuss is the reduction of contaminations, mainly from ambient sources and their impact on false discovery. Now, to do so, we performed a study in which we collected blanks and breath samples under normal conditions and then under extreme conditions of contamination. That contamination was controlled that we actually induced. And since we knew the components of that contamination, we were able to monitor those in different samples and learn from their behavior. Now, eucalyptol was one of those compounds, and we started the experiment by obtaining an ambient sample and a blank from Casper, showing that basically eucalyptol was absent. While on a breath sample, we see on-breath eucalyptol, which we'll refer to as the biological signal of interest. Now, when we introduced the contamination, we could see the positive control. The ambient concentration of eucalyptol is extremely high, and the following breath samples that were obtained still showed much similar concentration to the original biological signal when compared to the ambient concentration. However, to make sure we're not seeing some coincidental results, we took additional breath samples, however, this time allowing some leak into the system. It could be done by making a hole in the mask or releasing the mask for a few seconds. And we immediately saw that the breath concentration now, what we're measuring, reflects the concentration and variability of the ambient air in that room and not the biological signal itself. And this is how we learned that by using a receiver with Casper, we are able to eliminate high concentrations in the ambient. Our platform is basically resilient against ambient contamination. And as you can see here, false discovery, since the signal does not represent the biological signal anymore. Still within the sampling aspects, one question we had to answer is which part of the exhaled breath we are more interested in sampling. And we had two options. a whole breath, or also known in the literature as mixed, compared to the lower fraction of exhaled breath, which is known as the alveolar breath. Now, the main difference between the two is that the whole breath contains the dead space volume. And our concern was that due to differences in the anatomy and physiology of different people, including the dead space, might end up with variable dilution of the samples. So to test that, just like I showed you before, we performed a BOP study. We took 10 breath samples from a volunteer, and we used this very cool feature of receiver, allowing to capture different fractions of exhaled breath on different tubes. So one side collected the lower fraction, while the other side collected all the time to capture the whole exhaled breath from the very same exact breathing cycles. When we analyzed the data, just like I showed you, we used the formula of 3 standard deviation above the mean background to determine which compounds are on breath. We discovered that with the lower fraction, we get 36% more on-breath VOCs in our final output, as well as 55% lower in the variability in those samples. And that showed us that collection of the alveolar fraction of exhaled breath allows us better reproducibility, consistency, and lower variability. And therefore, it was our choice to continue using that fraction in the OMNI assay. We also validated those in a targeted analysis with 40 known on-breath compounds, and we saw a very similar result. Now, just worth mentioning that we need to keep in mind that sampling could be application dependent. So if we're looking into an oral disease, for example, we would be interested in collection of the dead space or VOCs that come from the oral cavity. And in that case, we could just change through the software of receiver to collect the whole breath or even only the upper part of the exhaled breath fraction. Still within a sampling, one of the questions was how do we optimize our sampling volume to maximize our performance metrics, the number of on-breath VOCs and their variability, as well as the analytical split. Now, as I said, for VOC to be considered on breath, it needs to be above the background. But first, it needs to be above the limit of detection. We need to see it first. And here's just a couple of examples on when we started testing for different volumes and splits to optimize the performance. There were 2 main patterns of behavior that we saw. On the right side, you could see compound that we saw for the first time with the optimized settings. It wasn't even detected before. Now we can see it in the breath sample. It's absent from the background, and therefore it's on breath VOC. On the left side, you could see compound that we saw previously with a lower volume, but the signal to background was poor. You could see that the concentrations overlap between the breath and the blank. And when optimizing for the volume and the split, we got a much better signal to background. And now it qualifies as on-breath compound that we could measure with the OMNI assay. And this is the type of development, and again, testing against the standardized metrics report and have data-driven decision-making by trying to improve the number of on-breath compounds and reducing their variability. Now, the other challenge that we discussed was regarding the analytical method and instrument variability and stability. And we tackled this in OMNI assay by introducing a very thorough quality control means. We introduced internal standards that are injected to every sample analyzed in the system. We have a ratio of 2 quality control samples for each analyzed breath sample in our sequences. We run 52 calibration curves every sequence for relevant VOCs that allows our application chemists to assess the sensitivity, limit of detection, linearity, and behavior of the instruments along the analysis sequences of clinical trials. And this is how it looks. So as I said, every sample is injected with 8 internal standards. We perform the sequence analysis, and by the end of the sequence, we have the output, the recovery, and variability of those internal standards. On the left side, you could see when the system is well behaving, a very low variability, about 5% RSD, within the limits of acceptance criteria. We're happy with it. We continue and run the following sequence. However, on the right side, we could see indications for when the system suffers from any problem that reflects on the variability and behavior of the internal standards. Now, we know that this would also reflect on the breath samples themselves. In that case, we stop, we test, we correct, and only when we meet the acceptance criteria, we continue to the following sequence. What that allows us is to keep the analytical variability as low as possible, spot problems in their early stages to correct. That improves our sample yield, because samples that fails the acceptance criteria typically are excluded from the statistical analysis, and therefore by spotting those problems early, we save as many samples as we could, and in general that improves the quality and the confidence that we see in the results and findings of those studies. The last aspect that I would like to share with you is regarding the data processing development for the OMNI assay. Now, this is a key step in which allows us to translate the data into information that we could use for statistical analysis, interpretation, and identification of potential biomarkers. And regardless of how well the platform is performing, errors in this step would lead to problems like false discovery, loss of potential biomarkers, low quality, irreplicable data, and basically faces in the clouds. Our chemoinformaticians team optimized this process and developed a tailor-made data processing for the OMNI assay, while still focusing on the same capability metrics that we discussed previously, the number of on-breath volatile organic compounds, their variability, as well as quality metrics specifically for this process. And what we see following the optimization of the parameters of the settings of those algorithms, that from the same set of data, we can now see more than double the number of on-breath VOCs that we detect across different samples. Now, those compounds did not just magically appear, but this is as a consequence of better sensitivity, selectivity, more accurate integration among or across different chromatograms, as well as we saw improvement in the quality. So the number of missing VOCs that the algorithm missed before is now reduced by 30%. Our ability to detect compounds that we know they are there is almost 98%. And we reduced the amount of manual intervention that required to correct errors in the data by over 20%. Now, if we zoom out and look into what this process provides, you can see clearly improvement in the biomarker discovery capability, as well as a higher quality and reliability of the data that gives us much more confidence when we discover potential biomarkers. So how does the data look from the OMNI assay, and what are our current capabilities? So to test this, just like I explained before about the BOP study, we did something similar here, a bit more challenging than typically, in which we took 57 exhaled breath samples from 4 different volunteers at 4 different days, equal number of representative system blanks for every volatile organic compound, started by looking into the blanks, understanding what the background is, and based on the formula, only ones that scored at least 3 standard deviations above that blank were considered on breath and being presented in this slide. So the median number of peaks or VOCs that we could detect per sample was 1,454. And from those, 517 in median were considered on breath based on that description in every sample. Now, if you look into this plot, it describes the repeatability of those volatile organic compounds across different samples. Now, for example, 266 volatile organic compounds were found on breath in at least 70% of the population here, which is the 57 samples, while 392 volatile organic compounds were found on breath in at least 50% of the samples, while 647 were found on breath in 25% of the samples, representative of a single volunteer in this case. In terms of top-level investigation of the data quality, a PCA for all of the analyzed samples shows that we easily distinguish between the different types of samples based on their content. We saw two clusters, one for breath in blue and one in orange for the system blanks, as well as a very interesting third cluster indicating the similarity between samples directly obtained from Casper and clean unused tubes, indicating how clean Casper air is, so it's not contributing more content to those tubes. To assess trends in the data that could be caused by analytical platform, every sample in the same PCA was now colored by the analytical sequence number, and we had over 20 sequences in this case. And you can see that there is a good distribution without any specific trends that could impact or explain the data and the output that we are seeing. To summarize, what makes the OMNI assay different? Well, I showed you how we optimize the sampling procedure in terms of volume and fraction, improving the signal to background, and having a wide range of exhaled VOCs captured and analyzed on the system. We've provided a platform that is resilient against environmental contaminants, which means we minimize the false discovery and minimize our variability. We have maximized the number of on-breath VOCs that we detect across different samples. We can measure now up to 500 on-breath VOCs per sample, as well as absolute quantification of 50 relevant VOCs in every sequence. We have minimized the end-to-end process variability, measurable by the internal standards, as you've seen. And we introduced a very thorough analytical quality control measures. Almost online, we could see every sequence and assess the performance of the platform. Plus, we provide an easy route to identification of novel compounds of interest through building our own high-resolution accurate mass library of standards and the utilization of the Orbitrap that allows easy and accurate identification. At the end, as I said previously, the OMNI assay is our signature biomarker discovery platform that we used for our internal research. We use with our collaborators and partners, as well as offer it as a service for biomarker discovery for our customers. It allows us a high-quality breath biomarker discovery studies and robust analysis of specific molecules of interest in the samples. Components of the end-to-end platform were characterized, developed, optimized, and verified against very robust product requirements, assuring all along that we maximize the number of on-breath compounds and minimize the variability of those compounds. After the introduction of the OMNI assay, the philosophy, the science, the development, and the capabilities, I would like to show you a snapshot from one of the case studies. This specific project was done in partnership with the Mayo Clinic. The objective was to identify and study breath VOCs that could be related to lung injury following an excessive physical stress. The population included 24 ultra-marathon runners that were tested before and after their racing. The samples were analyzed on the OMNI assay. 793 volatile organic compounds were detected and statistically investigated. The statistical analysis is summarized here in the volcano plot. Every dot reflects on a specific tested VOC. The x-axis reflects on the fold change. So positive means it was higher concentration post-race, while the negative on the x-axis means it was downregulated in terms of concentration post-race. We saw 161 volatile organic compounds that showed significant difference post-race compared to the baseline testing that was done with uncorrected p-value of 0.05. However, after correction for multiple testing, 63 compounds showed significant difference. 12 were downregulated, while 51 were upregulated post-race. Two examples of the behavior of VOCs, you could see that they're basically absent or at very, very low concentrations in our equipment blanks, the ambient air that was collected. So those are actually on breath VOCs, and we could see the significant difference between testing before and after the race. The results are still being investigated, and those compounds are being identified. In the meanwhile, we have identified some of those compounds due to their availability in the high-resolution accurate mass library. We could see here some alcohols and ketones that might be related to those results through pathways of aerobic and anaerobic metabolism, but still further work needed to link all of those 63 compounds to specific metabolism and potentially lung injury. In my last slide, I would like to share with you our vision regarding the future of breath analysis. We have recently kicked off the first human volatile sequencing project, in which we will identify every detectable on-breath VOC. And that would allow us to provide additional capabilities for biomarker discovery, mainly through the accurate, targeted global analysis approach for on-breath VOCs. That means we will be able to absolutely quantify each of those VOCs in every breath sample going forward in every project. That would allow us to build the largest database for exhaled VOCs in the world, including sources and related biological and metabolic pathways for each VOC, as well as a large pool of the absolute concentrations measured in thousands of patients from different diseases, demographics, and of course, access to comprehensive demographic and clinical data, which would further improve our capabilities to discover clinically valuable biomarkers for different diseases. Before I finish, I'd just like to thank the amazing team at Olson Medical for the development and the provision of the OMNI Assay for global VOC analysis. And of course, thank you all for listening.
Thank you, Morad, and a big thank you to Thermo, who sponsored this talk, but have also been wonderful partners during the development of the OMNI Assay. So we got time for some questions. Just a reminder to post it through the Q&A button. First one from me, Morad. So early on, when you're looking at some of the data for 1-butanol, so you're saying that it wasn't actually on breath by the definition of non-breath compound, but it was statistically significant when you look at the p-value. And as you say, you often find things reported in literature where it's statistically significant. So I was wondering if you could elaborate a little bit further on what some of the kind of dangers or challenges are on just relying on p-values, even if it's corrected p-values.
Yes, that's a really good question, Billy. I think the statistical test or the statistical approach should be fit for purpose for what we're looking for. And in this case, I don't think we're trying to say it is different or not different, which is what the typical t-test or non-parametric test would allow us to try and define. Still, we need to keep in mind that using unadjusted p-value, there is a really large space for error, mainly type 1 error. So therefore, we took it a little bit further, and we assumption that we have normal distribution, which we see in most of the background compounds. What we wanted to look into is make sure that we don't have the same distribution or even overlap between the signal and the background. And this is where the definition of standard deviation come from, because that means that there is no overlap between the signal and the background, and that discriminates that or eliminates the chances of random detection of false peaks in the data. As a general recommendation, adjustment for p-value, and in those cases actually to look not as a group to compare the mean and the variability, but actually what we're looking into here is the individual intensities of each of those VOCs, and make sure that as a group they are separated completely from the background noise.
Great. I think that answered one of the other questions around definition of on-breath compound. How confident are we that it's robust? So why 3 standard deviations, not 2, for instance? But I think that's largely covered. Next question is, so quite often what gets reported in literature is a particular sample collection analytical technique that's applied within a clinical study. And I think breath or blank type studies give a sense of what the base capability is, the end-to-end base capability. I'd be interested in your opinion about whether or not, as a whole within the field, we need to start reporting breath or blank type studies prior to undertaking clinical studies for, given sample collection analytical techniques.
I think this is a very important question that as a community we need to start trying to answer. How many volatile organic compounds we actually detect on breath? I mean, we've been studying this field for over 20 years now in the modern era, and I don't think we have a good question to which compounds are actually coming from breath. So I highly recommend the community to take this approach as a communication tool for us to say, this is what is expected to be found on breath. Of course, this is going to have some challenges with changes in ambient, in environmental, using different hardware for collection and even analytical methods. But if you think about the breath or blank method, it is very independent of how you actually collect and analyze the samples, because it's referring mainly looking into the background, understanding what it is, and then determine which of those compounds could actually reflect any metabolic or biological signals, and therefore worth minimizing my false discovery and focusing on those. And if we're already talking about this, the data that I presented today and studies that we have performed in the last almost 2 years showed us a very consistent picture of about 30 to 40% of VOCs that end up in breath samples don't have any signal to background, like one butanol. But if we look into the literature, I personally do not remember any paper suggesting such exclusion of such a great deal of what has been found. We typically see a couple of compounds identified in the background in a bag and excluded from the analysis. But I think still the risk for false discovery, mainly when we highly focus on multivariate analysis and combination of VOCs, at least one of them could be not from breath, and therefore the whole data will be non-irreplicable going forward.
Great. Next question is from Robert. Thanks for the inspiring talk. I'm guessing every omics researcher room wants to use the platform. My question is about those who can't. Is there any guidance or tips you'd want to give those who are setting up their own instrumentation and lab, just related to best practice, really?
Definitely. I relate to Robert's question here, and I think we all are working against some sort of uncertainty. I think what we need to do is to minimize the risk of the data we work with the results that we would like to publish or go forward and validate. Otherwise, I think the high percentage of failure or lack in replication and validation would remain very high. And that, of course, using representative blanks, for example, which is something that I focused on in this talk, For example, with Receiver, we're providing a clean inhaled air with Casper, and therefore the ambient sample per se is not representative of the rest of the hardware I'm using. And I see that a lot in publications. And therefore, it doesn't really represent my background and allow me to measure a signal to background. Again, the example with a p-value adjustment for multi-hypothesis testing, looking slightly differently and being a bit more harsh with the data, minimizes that false discovery. And of course, we need thorough confounding analysis just to make sure at the end that we don't have any better explanation to the results than the disease or the condition we are testing. So that includes analytical, pre-analytical variabilities and errors that might be introduced through the process of the study. Once we eliminate those and we still see VOCs that behave like potential biomarkers, then we minimize that uncertainty we're working against, Robert.
Excellent. Two questions from Olaf. One relates to which fraction of breath has been sampled. So you mentioned an emphasis on lower airways, but in some types of studies, oral cavity, etc., you might want whole breath or mixed breath. Olaf says many inflammatory processes have taken place in the larger bronchi, e.g. ozone, environmental pollutants, allergen, which causes airway inflammation. Exhaled nitric oxide is also mainly coming from the upper airways. Therefore, with respect to detecting airway inflammation, I'd not recommend to limit the sampling to the lower airway, which is a good point. And then his second question relating to the interpretation of the Mayo Clinic ultra-runner data could be related to lung injury, but also massive environmental exposure taking place. Where do they run? And massive metabolic changes during running. Therefore, interpretation will not be easy. Any thoughts on that?
Yes, I'll start with the second one. You're absolutely right. There are, although the main focus was on lung injury, but after you run such a long distance, the whole metabolism of the body actually changes. And it actually was reflected in the data by the amount of VOCs that we had statistical significance in. We started de-risking those compounds. I showed a couple of examples how those compounds were not found in the actual background, but we also found some exogenous compounds that had traces in the background. So this piece of work is still ongoing, investigation into the identity of the rest of the compounds, looking into the background and minimizing the risk of false discovery as well.
Thanks. Questions from?
For the first question, or Olaf, I absolutely agree, and that's why at the end of that specific slide, I mentioned that I don't think there are clear rules to how breath sampling should be. It is mainly application dependent. So if you're looking into an oral disease or upper airways, you would like to focus on the first part of exhaled breath or the whole exhaled breath, that actually makes perfect sense. In our approach, we wanted that balance between maximizing the number of on-breath detectable VOCs and minimizing the variability. And there's always a compromise. When you go with the dead space, you introduce higher variability for mainly compounds coming from the blood and the lower parts of the lung. And therefore, it's a balance and application dependent, but you're absolutely right.
Excellent. We have time for one or two quick ones. Next one's from Mark Willem. For the 517 VOCs that were reported, have you identified all of these VOCs by NIST or running reference standards? And could some of these be due to the interaction of the sorbent material and VOCs?
So for the first part of the question, as I mentioned in my very last slide, it's a project that we just kicked off. And we are actually working on true identification of all the on-breath VOCs that we measure with OMNI. And that's not through NIST library, but that's against actual running our own pure standards and validating their true identity. We do have tentative IDs, of course, for those through the NIST. And as you probably know, the probability or the confidence ranges from things that we're almost sure they are right to things or other compounds that we're not very certain about it. Regarding the source of those compounds, the representative blanks that I described should capture their origin. If those are coming from the tubes, so we sampled basically the ambient air going through Casper, driven to receiver, to the mask or mouthpiece, and then into the tubes. So if the main source of those compounds was actually the tubes or any other interaction, we'd probably see the same signal in breath and in blanks. But with 3 standard deviations above in the breath samples, I think it's really minimal risk that those compounds are actually contaminants from the system.
Thanks. And then last question, quick one from Sylvia. Great presentation, very convincing. Do you recommend replicate samples from each subject?
We typically, so with receiver, we collect 4 tubes from each, in each breath sampling. I think having more than 1 sample has several advantages. As a backup sample, things could happen, go wrong, mainly with GCMS. They know to fail at the most crucial times. So having a backup sample is a very good tool to maximize the sample yield by the end. The second utility that we typically use the other tubes that we collect is for the sake of identification of the compounds and validation of their identity going forward. So when we finish typical study, we have 10. But if we want to confirm the identity of those compounds, we could use the other duplicates or replicates from the breath samples to run them on chemical ionization, for example, MS if needed, and come up with their true identity at the end.
Excellent. Thank you, Morad. There's a few more questions being posted, but we can get answers posted across to the community for those afterwards. So thanks again for that.
My pleasure.
So, next up, delighted to welcome